Foxconn Quantum Computing Seminar. I'm Jello, and today we have the pleasure of having Dr. Seok-Hyung Lee. I hope I pronounced that correctly.
It's okay.
To give us a talk today on graph theoretical optimization of fusion-based graph state generation. So let me give a brief introduction to our speaker for today. Seok-Hyung is a research fellow currently at the Quantum Science Group, and this is in University of Sydney, which is led by Professor Stephen Bartlett and Professor Andrew Doherty. He did his PhD in Seoul National University under Professor Hyun Seok Young. His main research interest is in quantum error correction and photonic quantum computing, including the measurement and fusion-based quantum computing. And recently he has been leading a project which is on constructing a quantum computing architecture using color codes and developing their decoding scheme. Please, Seok-Hyung, the floor is yours.
Okay. Thank you so
Sorry
much.
to interrupt.
Ah.
I noticed that you are moving to Sydney, and I would also work from Sydney since July. So maybe we can have more conversations after the talk.
Yeah, sure.
Okay.
Yeah.
Good. So, sorry. Please start.
Yes. Okay. Thank you so much for inviting me to this seminar. Yeah. So as introduced by Jello, I'm Seok-Hyung Lee, and I'm currently a postdoc at the University of Sydney. And before that, I did my PhD at Seoul National University in South Korea. And today I'm gonna talk about a work I did during my PhD, graph theoretical optimization of fusion-based graph state generation, based on this paper that has been published in Quantum in 2023. Okay. And this talk will be structured as follows. First, I will describe the backgrounds of this work, including the definition of graph states and their basic properties, and also their applications to various quantum tasks, such as measurement-based and fusion-based quantum computing. And after that, I will talk about our strategy for fusion-based graph state generation, which is the main result of this work. Then I will show you some numerical results, and then if I have some left time, I'm going to demonstrate the Python library OptGraphState implementing our strategy. Yeah, let me begin with the backgrounds. For a given graph G with a vertex set V and an edge set E, we define a graph state as follows. We first place the plus state for each vertex of the graph, and then apply the control Z gate for each edge of the graph. So it can be mathematically written like this, where it is the unitary operator corresponding to CZ gate. And we consider this type of operator as V for each vertex of the graph, which is defined as the tensor product of the Pauli X operator on that vertex and the Z operators on the adjacent vertices of this vertex. So we call these operators as stabilizer generators, and the group generated by these operators are the stabilizer group of this graph state. In other words, this graph state is the common eigenstate of these stabilizers with eigenvalue of +1. So if we consider this kind of graph state, then this XZZZ is one example of these stabilizers. And some graph states are equivalent under local Clifford operations, and this equivalence relation is one of the most important parts of the theory of graph state. For each vertex of the graph, we define a Clifford operator like this, where, as the product of the minus pi over 2 rotation about the x-axis, and and pi over 2 rotation on the about the z-axis for the adjacent vertices. And And if you apply this operation to the graph state, then it is transformed into it is equivalent to transforming the graph into another graph, which is called this local complementation with respect to the vertex. And here, the local complementation is a kind of graph operation, and it is defined as follows. So local complementation with respect to a vertex V indicates an operation to connect every pair in the adjacent vertices of the vertex. For every pair of such vertices, connect them if they are disconnected and disconnect them if otherwise. For example, if we consider this graph state, then if we apply the local complementation with respect to this vertex, then it means that so these three are the adjacent vertices of V1. So this and this are not connected here, so it is now connected, and this is already connected. So here this is now unconnected. And it is important to note that by applying this Clifford operator to the graph state, we can transform the graph by this local complementation. And graph states are utilized in many quantum computing and quantum information processing tasks. First one is the measurement-based quantum computing, which is a well-known scheme of performing universal quantum computing by measuring qubits in a large 2D or 3D graph state. So initially, the 2D measurement-based quantum computing scheme was first proposed by Rausendorf and his colleagues, and they used this kind of 2D lattice graph state and show that it is enough to perform the universal quantum computing, but however, it lacks fault tolerance. And to be fault tolerant, we need to go to the 3D space and use a so-called Rausendorf-Harrington-Guéa lattice for the MBQC. And fusion-based quantum computing is a quantum computing scheme recently proposed by PsiQuantum. And unlike MBQC, it uses multiple small graph states, for example, this six-ring resource state. And quantum computing is done by applying two-body measurements called fusion between these graph states. And it is actually theoretically equivalent to MBQC, but it differs when we consider its implementation, especially in photonic systems. And it also used for quantum repeaters for long-range distribution of entanglement. And graph state, it is known that graph state can be used to increase the success probability. So, yeah. And besides that, the graph state can be used for various tasks such as quantum secret sharing and quantum metrology. And it is worth noting that graph states are suitable for photonic qubits, where the conventional gate-based approach is very difficult to implement for quantum computing. And so in those systems, MBQC and FBQC are more widely studied as a candidate for future fault-tolerant universal quantum computing. And also for quantum repeater, it is for quantum communication. So of course, photonic systems, we should use photonic systems for long-range communication. So it is, And these are some examples of well-known graph states which are particularly useful. Star graph state and cycle graph state are often used as Bayesian building blocks in MBQC and FBQC. In particular, the star graph state is known to be equivalent to GHZ state and also the complete graph state up to some local Clifford operations. And lattice graph state and these RHG lattices are used for MBQC. These are for 2D and for 3D. And 3D graph state, I even mentioned in the previous slide, but it is used for more fault-tolerant MBQC and FBQC through indirect measurements. And lastly, this is the graph state for quantum repeaters. Does anyone have questions so far? So yeah, please interrupt me anytime if you have questions. So to use this graph state, we need to know how to generate them. We can of course use control Z gate following their definitions, but it is quite tricky if you consider photonic systems because entangling gates between photons are very hard to implement. If we can use only linear optics, they can be done probabilistically with a very low success rate with 1/9 if you use single photon polarization qubits. And also, it cannot detect failure and photon loss without destroying the qubits. So it was one of the most biggest challenge when you want to implement photonic quantum computing. And then instead, we can use this type 2 fusion operation for generating graph state. And this type 2 fusion is basically not different from bare state measurement, but with a tiny modification of the physical Hadamard gate. And we can see that applying a fusion between two graph states, we can merge them into one graph state. In more details, by applying a fusion between these two vertices, we can connect every pair of the neighborhoods of this vertex and the neighborhood of this vertex. So we connect this vertex 2 and 1 prime and 4 and 1 prime. So it becomes like this. But we need to apply some Pauli modification based on the bare state measurement outcomes of the fusion. And this bare state measurement can be done only with linear optical elements and photodetectors. But it is still probabilistic, but have higher success rates compared to a bare control Z gate. Yeah, it is 50% if there are no additional resources for single photon polarization qubits and also other dual layer encoded qubits. And also, more importantly, it can detect failure and photon loss by the photodetector outcomes. So the error correction of failed fusions handling these failed fusion can be done more efficiently than using the direct control Z gate. So, however, the non-deterministic nature of fusions is still a significant obstacle when generating large graph state because it requires resources that grows exponentially as the number of fusions increase. Our motivation of this work was to answer the question of how to generate an arbitrary graph state through fusions from small graph resource state and how to optimize this process and calculate the resource overhead. Yeah, it was the backgrounds of our work. And now let's move on to the main part. Yeah, and so the basic resource state of our strategy is this 3-qubit star graph state, which is mathematically can be written like this, and graphically looks like this. And so these kind of resource states are the basic building blocks of this analysis. So our goal is to generate an arbitrary graph state by combining these 3-star graph states. And the resource overhead of a strategy is quantified by the average number of the Bayesian resource state required to successfully generate one copy of the desired graph state. And during the generation process, we take an approach that if a fusion fails, then we regenerate the state involved in the fusion and try it again, which is the method so-called multiplexing. And we repeat such processes until all the required fusions succeed. And the cost for such retrials are accounted for when calculating the resource overhead. And our strategy is summarized as follows. We first simplify the graph by unraveling process for various subgraph structures, and then construct a fusion network which instruct the required fusions between resource states, and then determine the time order of fusions, and we repeat these steps 1, 2, 3 for sufficient number of times, and select the one with the smallest resource overhead. And let's look into them one by one. The first one is the simplification.
Sorry,
yeah,
can I
yeah.
interrupt?
Sure, yeah.
I just wanted to understand, maybe you already mentioned, why is it natural to consider this the basic resource state?
So the basic resource state can be actually, it can be any small graph stage. In an extreme case, it can be just a single photon. But we are considering these 3-photon graph states because there have been many known proposals to generate this very basic 3-photon graph stage.
Okay. So the motivation is sort of like more based on what can be done in practice.
Yeah. There are even some deterministic schemes to generate this resource state, but of course using some nonlinear optics. Yeah. So by the way, this is just equivalent to the 3-qubit GHZ state, 3-photon GHZ state, which has been, there have been many experiments, generating such a state. So yeah. There is
Okay. Thank you.
Yeah. And the first step of our strategy is the simplification of the graph by unraveling process. And this unraveling means replacing a subgraph of a specific type with another subgraph that gives an equivalent graph state to the original one. And I'm going to elaborate this on the next slide with some examples. And we consider two types of subgraphs for this: bipartitely complete subgraphs and cliques. And let's begin with the first one, the unraveling bipartitely complete subgraphs. And here, bipartitely complete graph with parameter n, m is defined as a graph whose vertex set can be split into two disjoint subsets, V1 and V2, such that these two sets contains n and m vertices, and every pair in this set is connected. So, and this bipartitely complete subgraph just means the subgraph that is bipartitely complete. So this is one example of this bipartitely complete subgraph. We can see that this set of vertex and this vertex set are fully connected with each other, but we allow this kind of edge between vertices in each subset of each vertex set. And so if we can find this kind of structure in a graph state, then we can simplify the structure like this. So we introduced additional two vertices, V1 and V2, and these V1 and V2 are respectively connected with one of the two vertex set. And we can see that if you apply a fusion between these two vertex, then between these two vertices, then we can just recover the original subgraph. And this process reduces the original n edges to the n plus m edges and additional one fusion. And in our paper, we proposed an efficient algorithm to identify every non-overlapping BCS. And I'm not going to go in details about this, but I just want to mention that it has a time complexity of the number of vertices times the fourth power of the maximum degree of the graph. By the way, the degree of a vertex is defined as the number of edges that it is connected with. So we can do this in a polynomial time. And the second unraveling scheme is for cliques, which means the complete subgraphs where all vertices are completely connected. So, and we call a clique maximal if it cannot be enlarged by adding a new vertex. So in this example, these three vertices form a clique, but it is non-maximal since if we consider this additional vertex, then it can be enlarged. But these four vertices form a maximal clique because it cannot be enlarged. And if we can find such a structure in the graph state, then we first select one of the four vertices, then separate these. For example, let's assume that we select this V0. Then we separate this like this by adding 2 new vertices, then we can see that if you apply a fusion between these 2 vertices, then we can recover this state. And then we apply the local complementation with respect to this vertex. Then it becomes this one with some additional local Clifford operations. So overall, the initially n times n minus 1 over 2 edges is now reduced to n edges and additional 1 fusion and n local Clifford operations, which is much easier to implement. And so these two are unraveling schemes that we have currently. So in general, it'll be ideal if we can find an unraveling scheme for a general graph state. So in other words, if we can find the graph state that is equivalent to the original graph state, but is strictly simpler and equivalent under local Clifford operation. But unfortunately, it is known that it is a very difficult problem, and as far as I know, it is NP complete problem. So yeah, but anyway, if we can find some heuristic algorithms to do this in general, then it'll be very good. Yeah. So now we currently have these 2 schemes. By the way, there are known algorithms to find all maximal clicks, and it is known to be NP complete. But however, there exists an algorithm that can be run in a polynomial time in the number of clicks. So if there are limited number of clicks in the graph, then we can find all the maximal clicks quite efficiently. So in summary, the unraveling process indicates simplifying the graph with some vectors. Simplified graph, which is also called an unraveled graph, and additional fusion, which is also called external fusions, and local Clifford operations. And now let's move on to the next part, construction of fusion networks. So we now have unraveled graph state, and our goal is to combine multiple Bayesian resource states with fusions to generate this unraveled graph state. And a fusion network specifies an instruction for generating a desired graph state using, so if this fusion network is simply speaking, it is just a graph of multiple nodes and links, but we don't use the terms vertex and edges, vertices and edges, but the terms nodes and links because it can be confusing with the terms in the graph state. So each node of the fusion network indicates the Bayesian resource state, 3-qubit star graph state, and each link indicates the fusion required to the fusion that need to be done between these 2 nodes. And each link has is one of these 3 types: root and root to root, root to leaf, leaf to leaf, and indicates which pair of vertices we have to apply the fusion. So we say that the middle node, a middle vertex of the 3-qubit star graph state as a root vertex, and the other 2 as the leaf vertices. So, for example, if the link is root to root, then it means that we apply the fusion between the root vertex of this node and the root vertex of this node. So, if we can find this fusion network, then if you apply the fusion by following these instructions, then we can find this we can generate this unraveled graph state.
Sorry, quick question.
Yeah.
How do you determine which one is root, which one is leaf in the graph?
Both of these 2 are leaves. So you mean in the second case, root to leaf? I mean, both of these 2 vertices are leaf vertices, and so actually there are 4 types of links. So root to leaf and leaf to root. So we should identify. So we should specify the direction of the root to leaf links. So practically, I use some directed graph for this.
But I didn't see the direction here. You specified.
Here I didn't specify that.
Okay,
I see. But I remember that this fusion network doesn't contain root-to-leaf edges, root-to-leaf links. Yeah, but in general, some graphs can contain these leaves. Yeah, these links. Yeah.
So the direction is determined arbitrarily, or
it is fixed. It is fixed. Yeah, it is determined by the following process.
Oh, I see.
The process I mentioned in the next slide. Yeah.
Okay, thank you.
Mm-hmm. So the construction of the fusion network is actually quite straightforward. So let's say this is the unraveled graph state that we want to generate. Then we first decompose it into multiple star graph states like this. And you can observe that each star graph state corresponds to the vertices to a vertex of the original graph state with degree larger than 2. So these vertex 4 and 5 corresponds to this kind of vertices. So we can consider 2 star graphs. And if you apply a fusion on these 2 vertices, then we can recover this graph state. And after that, by the way, this fusion is leaf-to-leaf fusion. So it corresponds to leaf-to-leaf link. And after that, we decompose each star graph state into multiple basic resource states. For example, this 5 qubit star graph state can be decomposed into these three Bayesian resource states with 2 fusions. So you can observe that this root vertex of the star graph state is this one, and the root vertices of the other two resource states are participating in a fusion, and these 4 leaf states are the leaf stage of these 3 resource states, Bayesian resource states. And each of the fusions are root-to-leaf links. And we can do the similar thing for these 4 vertex star graph state like this. And then we can convert these relations, this construction, to a fusion network. And it consists of 5 nodes, and each links has types like this: root-to-leaf, root-to-leaf, leaf-to-leaf, and root-to-leaf. Yeah. And also the unraveled graph state also can contain some external fusion, which are originated from from unraveling BCS or cliques. So if we suppose that there is an external fusion between these two qubits, 1 and 6, then it is just expressed in the final fusion network like this, just between 2 nodes with an additional link. And it is important to note that these fusion networks are not unique for a given graph state. For this example, this is another fusion network that gives the same graph state, and this is possible because the leaf qubits of a star graph state are symmetric. So in other words, if we considering this star graph state, it has a symmetry under the rotation under the permutation of these 4 leaf qubits. So after decomposing it like this, we can assign these 4 vertices arbitrarily to these 4 possible leaf qubits. So in this example, we assigned like this: 1, 2, 3, A2, 1, 2, 3, A. But in the previous examples, we assigned like 1, 2, 3, A2, 1, 2, 3, A. So we have a degree of freedom of choosing these leaf qubits after the decomposition, and it gives different fusion networks in the final stage. Yeah, but actually we don't have a clear strategy to select between multiple fusion networks, but we just use a randomization technique. In other words, in each trial, we just compute the resource overhead for a randomly chosen fusion network, and we repeat this multiple times and select the best one. So it'll be very useful if you can find some optimization technique for this, but for now, we don't have it now.
Sorry, I have a question.
Yeah.
So when you, I mean, like, as you said that it will not be unique. So as long as you have same number of fusions, it doesn't matter which one you choose.
No, that's a very good question, but actually it matters. So it seems that, so both of them have the same number of fusions. It has 4 fusions and it has 4 fusions, but their resource cost can differ by this. And I will talk about it in the next stage, the determination of fusion order.
Okay.
So if we consider, I mean, the repeat until success strategy, I mean, so if we take an approach to perform all the fusions at once, then just post-select the graph state, post-select the outcome state. If all the fusions succeed, then it will be the same. They will give the same resource cost. But our approach is a little bit different. We will perform the fusions step by step, and then if a fusion fails, then we discard the qubits that is involved in the fusion. But qubits that are not involved, photons that are not involved in the failed fusions are not discarded in this process. So if you take this approach, then it will definitely reduce the resource cost compared to just take a repeat until success property at a whole. But the way to determine the fusion network makes this resource cost different.
Yes. I mean, like, because it just gave me the impression that this is sort of like a more like there's a part of it that's like art more than science. So like there's ways to do it, but it's not immediately obvious which one is the most optimal one, and you sort of have to kind of try and see which one is the best. Okay. Yeah. But anyway, I should let you continue.
Yeah, actually, I agree. That's the big point of this work, actually. Yeah, so our strategy is very heuristic because it is very, very difficult to consider everything and optimize everything. Yeah, so yeah, it'd be worth investigating if we can find some physical intuitions for this. But yeah. Anyway, the next step is about determining fusion order. So so given the fusion network, we can always generate the desired graph state if all the fusions succeed. But we need to care their order because the fusions are probabilistic, and so the resource overhead varies depending on which one to perform first. And for this optimization, we regard the fusion network as a weighted graph of multiple nodes, and each node corresponds to a group of entangled qubits, and of course, it is initially just the 3 Bayesian resource stage, and each link corresponds to a fusion between these groups that need to be done. And we assign the weight on each node, which is initialized to +1, and it means the average number of required resource states to generate the entangled state on the qubits of the node. So, for example, if we consider this fusion network, then each node of this network has the weight of +1 initially. And by viewing this fusion network as a very graph state, we can regard the conducting of a fusion as a link contraction process. In other words, conducting a fusion between 2 nodes indicate entangling the photons in these 2 nodes. So it means combining these 2 nodes into one single node. And if a link is contracted, we assign the new weight. We assign the weight on the new node like this, where it means that for example, contracting these two nodes make this this new node with weight 4 when the success rate of the fusion is 50%. And it means that to generate the entangled state corresponding to this node, we need 4 Bayesian resource states in average, because this fusion fails in 50%. And by repeating this process of link contraction until we have only no links in the fusion networks, the resource cost of this process can be determined by the summation of the weights of the last remaining nodes. So in this example, the final node have the weight of 16, so we can say that its resource cost is 16, which means that we averagely need 16 Bayesian resource states in this generation process. And one thing to note here is that links that do not have common nodes can be contracted at the same time. So in this process, this contraction and this contraction are actually done in different pairs of nodes. So this is actually originated from this node, this link. So and this contraction and this contraction. So the order between them doesn't matter. It doesn't matter if we contract it first, then this one, or contract this one first, then this one. We will always obtain the same fusion networks. So we can regard them to be done in parallel. Now, going back to the problem of determining the fusion order, we can do this based on 2 intuitions. The first one is that it is better to contract links with smaller weight first. So if we consider this example, and let's say we already contract the first link like this, so obtain these two this fusion network. By the way, the weight of a link is just defined as the link as the weight of the new vertex if after contracting the link. So this link has the weight of 4 because if we contract these two nodes, it will make a node with weight 4. So here we have two choices. We can contract this one first or this one first. But if we contract the second link, then it will give the weight of 16. But if you contract the first link, then the weight is 22. And so the first choice is of course better because it gives lower resource cost. And here I just showed a simple example, but generally we can prove that contracting links with smaller weight is always better. And the second intuition is that it is better to contract links in parallel as much as possible. So if you consider these 2 examples, where the first one is contracting this one and this one at the same time first, but the second one is contracting the middle link first, then in the final stage, the first one gives lower resource cost, and it is because we perform the 2 parallel contractions at the same time in the first stage. And based on these 2 intuitions, we propose the so-called mean weight maximum matching for strategy, which is basically just just using these 2 intuitions. So we first find the set of links with the small least weight. So for example, if we want to contract this one, then sorry, I didn't write the weight of edges here. But anyway, so we first find the set of links with the small least weight, and then obtain the subgraph of the fusion network induced by these links. And after that, we find the maximum matching of the subgraph, and here the maximum matching is just the maximum set of links without common vertices. So basically, it means the set of links that can be contracted at the same time. And after finding this matching, we contract all the links in the matching in parallel, and we'll repeat this process until the fusion network contains no links. And by the way, this finding maximum matching can be done in a parallel in the polynomial time on the set of number of vertices and edges. So it can be done quite efficiently. Yeah, so summary of our strategy can be summarized as follows. We first simplify the graph by so-called unraveling process, and we considered two types of subgraphs here, bipartitely complete subgraphs and cliques. And after that, we construct a fusion network that to generate the unraveled graph state, which instruct the required fusions. And of course, it contains some randomization process because the fusion networks are not unique for a given graph state. And we then determine the fusion order based on the aforementioned strategy. And so these three are a single sample of the strategy, and we actually iterate these 3 steps a sufficient number of times and select the ones with the smallest weight and smallest resource cost. And let's move on to some numerical results. We first did some analysis on random graphs with fixed number of vertices and edges. So this graph shows the resource cost against the number of edges. Actually, this is a ratio of the number of edges and the maximum number of edges, which is like this. And each line corresponds to different number of vertices. And these two corresponds to different fusion success rate. And I like to note that this 50% of success rate can be accomplished by using without any ancillary photons and using only on-off detectors, while this one can be reached by using some ancillary photons and photon number reserving detectors. And it is not surprising that this resource cost increase exponentially as the number of vertices increases like this. So even though we optimized through our strategy, it requires quite a large amount of resource cost. For example, if you want to generate the graph state with 24 vertices, then it requires about 10 to the 6 resource cost. 10 to the 6 the Bayesian resource state. And one interesting point here is that this resource cost is maximized when this ratio is around 60%. And we currently don't have a clear explanation on this, but we guess that it might be related to the entanglement of the graph state, but we are currently not sure, so it will be worth investigating. Next, we also wanted to test if this strategy is really effective. And for this, we compare our full strategy with the ones without, with some deficient strategy with some where a specific part of the strategy is omitted. The strategy 1 is the strategy without unraveling, and the second strategy is just selecting fusion order randomly without the strategy. And the third one is just the first strategy. And we showed that this first strategy before that this graph shows the resource cost of for different number of vertices, and this P is the ratio between the number of edges and the maximum number of edges, so different number of edges. And we clearly showed that our first strategy is significantly resource efficient than the other two. So it implies that every stage of our strategy is indeed essential for minimizing the resource overhead. So, and here are the summaries. So graph stage, are also resource stage for various quantum information tasks such as MBQC and FBQC, quantum repeaters, and quantum metrology. And especially they are useful for photonic systems, because conventional gate-based quantum computing is quite difficult in photonic with photonic qubits. So it is very important to generate linear optical. It is very important to generate photonic graph state especially using linear optical devices. But the problem is that graph state, the type 2 fusion operations, which are commonly used for generating graph states, are probabilistic. So if there are no additional resource states, they succeed at the rate of 50%. So large graph states are difficult to generate. So we proposed a kind of heuristic graph theoretical strategy to effectively optimize the generation of any graph state by type 2 fusion operations. And the main idea, actually, we think that the first process of unraveling graph state is the main part of this of our strategy. So it's in the case to find the graph state equivalent to the desired graph state under local Clifford gates and type 2 fusions, but easier to generate. So we expect that this strategy and also we developed the strategy of graph state through Python, and we expect that they will assist other researchers in developing and accessing some schemes using photonic graph state. And I like to demonstrate the library very, very quickly. So yeah, this is the Python package of our library of OptGraphState. So it is a package that implements this strategy to optimize the generation of any graph state. So I just prepare a simple notebook for this. So this is the line for. So we are now considering the lattice graph state with parameter 4x4, which means that you can draw the graph state like this using this command. So it is just this 2D lattice graph state with 4x4. And then if we can simply implement that strategy by using this code line, where it means that we consider 1,000 trials, 1,000 samples to find the optimal strategy, and with the fusion success rate of 50%. Can run it. Then it's just that the best overhead, the resource cost, is about 8,000, and the number of fusions required for this is about 5,000. And this number of steps means the number of steps. The number of group of fusions that can be done in parallel. So we need at least 9 steps here. And this is the unraveled graph for this. So this lattice graph state becomes this kind of very strangely looking graph state by unraveling. By the way, this red dashed lines means the external fusion, which means that if you apply the fusions between, if you apply a fusion for each of these red lines, then it will recover this original lattice graph state. And this is the fusion network for this. Yeah. So this node, this circle means each circle means a node, which indicates the Beijing resource state, and these are linked. And this number on the link indicates the fusion order for the optimal way to generate the resource, the desired graph state. So, for example, we first apply fusion on the link written that 1 is written, and then 2, and so on. And the type of links are shown as the line stars. For example, these blank lines indicate leaf-to-leaf edges, leaf-to-leaf links, and these red lines indicate root-to-root links. And it doesn't contain any leaf-to-root links here. So, yeah. Yeah. So this was a simple demonstration of the code of the library. And yeah.
Can I have a
Is
quick
any-
question on
Yeah,
that?
yeah, sure.
Okay, I don't know if it will happen, but suppose you have some graph state where there's two equally good solutions. So your software will give just one of them or both of them?
One of them. So it is just a heuristic thing. So yeah. So it just use some randomization process here. So so yeah, of course there can be some two or more strategy that gives the same resource overhead. Yeah, but this strategy, this library just choose one of them randomly. I think they choose the first one for the first sample. Yeah.
Okay.
Yeah. So I like to mention that I like to emphasize that all these strategies are actually quite heuristic. So, and it is not quite based on some physical intuition. So it will be very worth investigating if we can find some physical intuitions or other better strategy or more general strategy for this. So, yeah. And any other questions?
Okay. I guess thank you for the wonderful and informative talk. So now we have some time for questions.
I have a question about the fusion. So in your process, you limit the number of nodes that can be connected through the fusion, right? I mean, there should be some limitation of the fusion you choose. The nodes they can connect are like up to 3 or 4 nodes, for example. So what's the limitation of the fusion, and how do we implement them physically?
I'm not sure I fully understood your questions, but so a fusion itself is just implemented between two photons. So if you consider this fusion network, a single node can be connected with at most 3 nodes, because each resource state is composed of three qubits, which are just 3 photons. So each of them it can be only involved in at most 3 fusions for each of them, and each fusion can be implemented using these linear optical circuits. So this one and these ones are two input photons. Yeah, of course it is for single photon polarization qubits, so it is a bit different for different other dual layer encoding qubit. But yeah, these are wave plates for this, which rotate the polarization angles of the qubits, and these are polarizing beam splitter, which pass where the photon passes through it directly when it is horizontally polarized, and it is reflected if it is vertically polarized. And these are photodetectors, which detects where there is a photon or not. So we have some photodetector patterns that can determine the success of the fusion process. Yeah, and if it succeeds, then we can do this merging process. Yeah.
So in each fusion, there is some probability that it can fail, right? So you can only continue for every step to succeed.
That's true. That's correct. Yeah. So in this fusion network, so let's consider this one. Yeah. So in this process, so if we perform this fusion and if it fails, then we regenerate these two resource states again, and then retry the fusion. So after doing this, then we obtain this one. Yeah, we obtain this one. Then if this fusion fails, then we discard only these two photons, and then we generate this again, like this. So, and for example, if this fusion fails, then we need to regenerate all of them at the beginning, from the beginning. Yeah.
I see. Okay, thank you.
Yeah. Thank you.
Okay, I don't know if there's any other questions. Maybe I can ask one thing. So for some family of graph states, can you prove that your strategy is optimal?
Oh, that's a very good question. I'm currently not sure about that. We haven't tried that, but yeah, that will be very worth investigating. So for a very simple graph state, especially for these types of well-known graph state, I think for this kind of very simple graph states, 3-vertex cycle graph state, I think we can prove easily, because the number of possible strategies is not very large. Yeah. So yeah. Currently, I'm not sure, but it'll be it'll be worth investigating. Yeah.
Yeah. Okay. Yeah, I mean, I imagine, that's something one has to think about.
Yeah, I agree.
I have a question.
Yes.
I just wonder, your approach is heuristic, so it means that you cannot determine which one is the optimal, but can you guarantee that the process can succeed anyway?
Yeah. You mean so? You mean the success of the strategy itself, or generation of the graph state?
Generation of the graph state.
Yeah. If we can supply sufficiently many Beijing resource states, then we can guarantee success. Yeah, but so this resource cost indicates the average number of required resource states. So aware, of course, yeah. So it can go to infinity, but such a probability will converge to 0. Yeah. So yeah. Anyway, yeah. So I can say that we can always succeed if we have sufficiently many resource states. Yeah.
I see. Thank you.
Yeah. Thank you.
Okay, maybe one more question. Does one have?
Yes, I have a question. Like in your demonstration, you show the best overhead of the generate this kind of state. So could I ask what the specific this value means? Like this 7,680.
This one. So it is simply speaking, it is the average number of Beijing resource states required to generate this one. So to generate this 3x3 lattice graph state, we need about 8,000 three GHG state, 3 photon GHG state, if the fusion success rate is 50%. So it seems very large, but actually the fusion success rate of 75% is more widely used recently. So I mean, it only needs 2 additional photons per fusions. It takes quite a time.
Okay, thank you.
Yeah, so I think we can. Yeah, if we increase like they only need 200 Beijing resource state, so it is a very dramatic difference. Yeah.
Okay, I guess that's all of the questions. Okay, thank you again for the wonderful talk. I'll stop the recording here.